Hello, everyone. Welcome back to the thermodynamics module of this course. So first, what is thermodynamics? Thermodynamics is the science that was developed back in the 19th century to describe the basic operating principles of the newly invented steam engine back then, right? Thermodynamics, thermal means heat. Dynamics means power. So thermodynamics really describe how one can convert heat to power, which is the purpose of the steam engine, right? So really, thermodynamics define the concepts of energy and equilibrium, and it describes how systems interact with their surroundings and the equilibrium states that the system will eventually reach and stop to change. So in the in today's lecture, we will go into define what system is and what are the surroundings and the what are the equilibrium state. Okay. Now, in this particular module, we will have like 5 lectures in total. Lecture 1 will focus on the foundation of the thermodynamics and the first law of thermodynamics. Lecture 2 will focus on the second law and entropy. Lecture 3 will focus on thermodynamic properties of fluids and also equations of state. Lecture 4 will focus on phase equilibrium and thermodynamic models, and Lecture 5 will focus on heat effects and chemical reaction equilibrium. All right, in this particular module, the course material, we are going to refer to this textbook. The title is Introduction to Chemical Engineering Thermodynamics by Smith et al. And then this book is 9th edition. If you send me an email, I can borrow you a hard copy if needed, okay? All right, so today's lecture, lecture 1, is really going to focus on the foundations of thermodynamics and the first law. So by the end of this lecture, you should be able to establish the physical basis and also the importance of the thermodynamics in most chemical engineering processes, okay? So we will first do a little bit definitions in terms of like systems, surrounding, and also state functions, and really talk about like different types of thermodynamic properties. And then went ahead to talk about thermodynamic equilibrium, and then really spend time on discussing the first law of thermodynamics. And also path and state functions, right? If we apply the first law, we can actually apply to a closed system, such as piston cylinder problems. Okay. All right, let's jump in. So really, thermodynamics involves like the science describing the phase changes, energy conversion, and reaction equilibrium. All these processes are highly relevant in the typical chemical engineering processes, okay? Now, if you imagine in chemical engineering plant, you will have a lot of like condenser, pump, boiler, right? And then turbine engine, and then the turbine will have some like motion to convert like mechanical work to electricity, right? So all throughout these processes, right? You could imagine condenser is trying to condense vapor to liquid, and then the pump will pump the liquid into a boiler. Boiler really is like converting the liquid to vapor. So in these two, right, boiler and condenser, you are really talking about phase changes. For example, liquid water to water vapor, right? Water vapor condense here into liquid water, and then liquid water evaporate, boils into water vapor, and then like move the turbine engine, right? Now, and also for this boiler heating process, where you are actually talking about reaction. You have fuel and air, and then they combust. It's called a combustion reaction. And then because of this combustion, you generate a lot of heat. And then heat is, absorbed by liquid water, and then liquid water evaporate, right? So here we are going to talk about combustion reaction in this module as well. And then really we are going to talk about reaction equilibrium associated with these processes, right? And at the end, right, we are always going to talk about energy conversion, right? Either like heat converting to work or work converting to electricity, right? So all these different types of like energy conversion is governed by the first law of thermodynamics, meaning the energy is conserved, okay? All right, so before we jump into discuss the first law of thermodynamics, we actually need to make some definitions, right? First, we need to define what a system is, okay? So by definition, the system is a collection of material or space in which a process occurs. So if you imagine, you can have like an imaginary boundary. It could be physical or imaginary, but you just like define, right? This is like actually a collection of the materials or space that we are going to focus on. And then what we are going to study is that what like the change of this system, meaning the process, okay? Now, once we define the system, you can actually just like define surroundings by basically just like everything not included in the system. Basically everything else surrounding this particular system that you selected at the beginning, okay? And then between system and surroundings, obviously, you can see this is a boundary, right? So like I mentioned, the boundary is basically serving as the interface between the system and the surroundings. And like I mentioned, this could be imaginary or physical, right? And we will give you some examples in a moment, so bear with me. Now, we already defined the system, defined the surrounding, defined the boundary. So now we can actually talk about different types of system, okay? So there are three types of systems. The first one is open system. An open system is a system with a boundary which allows mass or and energy to flow between surroundings and the system. So basically, so if you say this system is open, you can actually have energy or heat flow into the system or out of the system. And you can also do some like mass transfer. So you actually have like different mass flow between the system and surrounding. Now, if we are talking about closed system, then closed system is basically the system with a boundary only permits energy flow. So basically there is no mass flow between the system and the surroundings. So the total number or total modes of species inside the system doesn't change, okay? Or their identity doesn't change, meaning that we have fixed contents in the closed system, okay? And then the last one is the insulated system. Insulated system is basically a system with a boundary that cannot allow both mass and energy to flow through the interface. Okay, so meaning impermeable to mass and energy flow. So not only the contents in the system is going to be remain the same, but also the energy, right, or the heat doesn't transfer between the system and surroundings. So it's actually an insulated system. Okay. Now, like I promised, I'm going to show you some examples of different types of system. So the first one is open system. If you imagine a human body, right, you are constantly inhaling oxygen and then give out carbon dioxide, right? So here, if you select human or yourself as a system, then everything else will be your surrounding, basically the air surrounding you, right? And then, so between surrounding and the system, which is our body, you can see, right, oxygen goes in, CO2 goes out. So actually the content within the system is actually changing, right? So basically you have mass flow between the system and the surrounding. And the same thing, right? You are inhaling the temperature of the air you are inhaling is probably room temperature, which is 25 degrees C, right? And then when you go through the body and then when you exhale out, right, then the CO2 will have some temperature heated up by yourself, right? So basically, you also involve the energy transfer between your system and the surrounding, right? And like I mentioned, right, the body temperature is 37 degrees C, room temperature is usually 25 degrees C. So there are some heat thermal gradient between the system and the surrounding. So for open system, we can actually allow the energy transfer, okay? Now for closed system meaning that the content inside the system is going to be fixed, right? So if you can imagine a balloon and then you really wrap it up very tight, and then the air within the balloon is not leaking, although it will leak slowly, but within the time scale that we are talking about, we just assume it's not changing, okay? It's not leaking. And then when it's in this particular case, then the balloon or the air inside the balloon is not going to change. So basically you have fixed content. So basically it's a closed system. But now for the balloon and the surrounding is your air, again, you may have some energy change, right? So inside, right, if you have like a different, when you have a balloon, you keep rising to the top, right? And then you may have some energy, like when it's getting colder, they may shrink, right? So when they go get hotter, they may expand. So basically, depending on your surrounding atmosphere, your balloon will have like different energy state, and then you may pop open, right, under certain circumstances, right? So in this particular case, this is a closed system, which doesn't allow the mass to transfer between the system and the surrounding, but allows energy to still transfer, okay? All right, the final one is insulated system. Insulated system, you could imagine, right? It's really tightly sealed water thermostat, thermal cup, right? And then you really seal it tight, and then the water doesn't evaporate. So water, liquid water inside is not changing. So the fixed content. And then since it's like really wrapped up by these vacuum steel, like those kind of thing, and then basically it doesn't allow the heat to transfer, right? So in the end, this is going to be an insulated system. So hope by now you can understand the definition of the system and also different types of the system that you are dealing with in the on a daily basis. Okay. So now we define the system, we understand the surrounding, and then we talked about different type of system, and then we can actually think about what is the interactions, right, between the system and the surrounding. So the first interaction is going to be related to the mass transfer across the boundary for open system, right? Like I said, for open system, you can allow mass transfer. So when the surrounding and the system is exchanging mass or components, right, then that's an interaction, okay? So this is one way for these two to interact, okay? And then the second way to interact is the displacement of the boundary. And by this displacement, you're actually doing mechanical work. Usually we use W to represent mechanical work. So if you would imagine a piston, and then you have some gas inside, okay? So this piston, you can compress, you can release. So by when you are like compressing the gas, which is like the gas inside, and then you can pick this as your system, okay? And then when you like, compress the piston, so the piston move down and then you are compressing the gas, right? So the total volume of the system is going to decrease. But since this is like a closed system, right? So you are not changing the content inside the system. So you will have some like, a higher energy state, which we will talk about that later, okay? So, but by displacing this mechanical, displacing this boundary, right? Boundary is like basically this is your surrounding, and then this is your system, this is your boundary. By displacing your boundary, you are actually doing mechanical work on your system, or your system is doing mechanical work on the surrounding if they are expanding. Okay. And then the last one is obviously the heat transfer across the boundary. And we usually use Q to represent the heat, okay? And then in the previous balloon case, right, if your air in your surrounding gets hotter, right, then you are actually going to input, flow in some energy into the system, right? So you can actually have some Q or heat transfer, okay? All right, so now if perfectly insulating boundary, then usually we call it an adiabatic system or adiabatic process. When we talk about adiabatic, then Q is equal to 0, okay? So no heat exchange between the system and the surrounding. So it's an adiabatic system, okay? All right. So now we have defined, right, what system is, what surrounding is, and what is the interaction between the system and surrounding. And now we can actually start talking about the first law of thermodynamics for a closed system. Okay, so here we are talking about closed system specifically, meaning that you have fixed content within that system. Okay. So the first law, the statement of first law of thermodynamics, let's just read it. It's although energy assumes many forms, the total quantity of energy is constant. And when energy disappears in one form could be heat, could be work, right? And then it appears simultaneously in other forms, meaning that like, the total energy, total quantity of the energy is constant, right? So energy is conserved. Like this is essentially the first law of thermodynamics, okay, for a closed system. And then when we are talking about mathematic form of the first law, it's basically delta E system is equal to Q plus W, right? Delta means change. E means energy. E system means energy of the system. And the delta E means the change in the system energy, okay? And then coming back to this piston example, right? If you select the air inside the piston as a system, and then we are trying to study its energy change, right? Previously, we talked about there are two interactions. One is mechanical work. If it's compressing, then the system is doing work on the system, right? So you will have a W. And then if the heat is flowing from the surrounding to the system, then you will have a Q flowing. So in the end, your delta E change in your energy of the system is equal to just like Q plus W, right? There are no additional energy forms exchange with the system. So this is the first law of thermodynamics, right? Delta E system is equal to Q plus W. Q is the heat, W is the mechanical work, okay? Now, if you zoom in to the system, right, this is a macroscopic view, and then overall view, right? And then if you zoom in this system, the system energy or total energy is usually considered consists of three parts, right? First is the internal energy. Internal energy quantifies like the molecular interactions within the molecules inside the system, okay? That's called internal energy. And then there are some kinetic energy, right? Kinetic energy meaning that like the whole system, if it's moving at a speed, then you have like some kinetic energy. And then potential energy is that, let's say if your system is at a particular like height, then you will have some potential energy, okay? So total energy equal to internal energy plus EK plus EP. And usually in most chemical engineering processes, these two are negligible. So basically we don't need, we only need to consider internal energy. And internal energy is related to temperature and pressure of your system, okay? And we will give you more details on this slide here. All right, here let's talk about like this energy, total energy, internal energy plus kinetic energy plus potential energy, right? Give you example here. If you think about a balloon here rising into the sky, okay? So you release it and then the air inside, let's say, is helium, and then basically you have a lower density than surrounding air, and then it will rise, okay? Now, if you have the balloon go slowly rising, right? So you are increasing in height. So your potential energy is increasing. And then because this whole balloon is moving at a speed of v, then you will have like some kinetic energy. And then internal energy is really, we are talking about the gas molecule interaction within this system, internal system. Okay, so it's internal energy. All right. So the total energy of the system, like I mentioned, we have macroscopic forms, which are kinetic energy and potential energy, right? And then we also have microscopic forms, which are internal energy, right? Internal energy also consists of intramolecular interaction. So basically, the interaction within the molecule by itself, okay? It's called like could be kinetic, vibrational, rotational energy. And then you also have intermolecular interaction, meaning the interaction between this molecule and this molecule. So this will actually depends on temperature and pressure of the system. So your internal energy will depend on temperature and pressure, and we will give you more details in the next few lectures. Okay. And this is microscopic form, right? Macroscopic form is more straightforward. We should already learn this in high school, right? So kinetic energy is EK is just equal to 1/2 times mass times velocity squared, right? And then potential energy is basically just mass times gravitational constant times z, right? It increases with z, increasing with v here, right? So depending on your v and z, you will have different macroscopic forms of energy, okay? Now, like coming back to this first law of thermodynamics, right? Delta E, we can rewrite into delta U plus delta EK plus delta EP equal to Q plus W, right? Now, for most chemical engineering closed system, for example, a compressor or boiler, right? This boiler is not like moving, like the whole, like, right? So, and then like the boiler, usually we sit on the ground, right? So in this case, right? Basically, for most chemical engineering processes, right, delta EK is usually 0. Delta EP is usually 0, right? If we run at a steady state, usually these two will be 0. So eventually, right, this equation can be simplified into delta U. The internal energy change is equal to Q plus W. Right? This is applicable for most closed chemical engineering system that you usually run into in all your chemical engineering courses. Okay, so delta U equal to Q plus W. Okay, first law of thermodynamics. And then this is like the integrated form. And then you can also have a differential form, right? We are replacing this delta with D. D means differential, like really tiny change in internal energy is equal to dQ plus dW, right? So basically, this is the differential form of our first law of thermodynamics, okay? du equal to dq plus dw. Now, we need to define some conventions, sign conventions, right? So when we are talking about Q, like the sign of Q or dq, right? If we are talking about like a system, right? If we have like heat flow into the system through the boundary, then we assign dq is greater than 0. So you have heat flow in from the boundary, from the surrounding to the system, okay? So heat flow in through the boundary dq is greater than 0. On the other hand, if we have heat flow out through the boundaries, then we have like dq is less than 0. So you have heat flowing out, okay? So dq is smaller than 0. So you can think like this, right? When we have heat flowing from the surrounding to the system is absorbing heat from the surrounding. So its internal energy is increasing, right? So that's why we are using like dq positive, because it causes an increase in the internal energy. Vice versa, right? For dq is negative for heat flow out, because the system now is giving out heat by reducing its, and as a result, it reduces its internal energy, okay? All right, if you don't have any heat exchange, then obviously this dq is going to be equal to 0. And then this is like what we are talking about, like it's an adiabatic process, right? It's a perfectly insulating wall that doesn't allow energy to permeate, okay? So dq is equal to 0 for adiabatic process, okay? Now the second one, so we already talked about Q, and then now we need to talk about dW, right? So work, dW, is usually related to the pressure volume, right? So coming back to this piston example, we are compressing the gas. All the gas is expanding and pushing the piston out, right? So really, you have a pressure associated with this surrounding and the pressure of the system, right? Depending on which one is bigger, you can move one way or another, right? Now, speaking of sign convention, right? If we are thinking about expansion, right? Expansion meaning that the V is greater than 0 or positive, so it's expanding. Okay, so the piston is moving this way. And then in this particular case, we are going to assign the W is going to be negative. Okay, so now the way you can think about this is that, so we are talking about internal energy of the system, right? When we are expanding, right? If you go back to this example, if we are expanding, then the molecule distance between each other will be increasing, right? If they are increasing in distance, then the interaction or intermolecular interaction is going to drop, right? When this intermolecular interaction is dropping, then your internal energy is dropping. So that's why, right, when you are doing expansion, right, your internal energy is dropping. So relatedly, right, your dW is negative, right? So that's why we assign expansion, dW is negative, right? Because the overall effect is that your internal energy of the system is dropping, okay? And then on the other hand, if you are doing a compression, then you are really compressing the gas. dV is negative. And then in the end, dW is positive, right? Because you are, your internal energy now is going to be increasing, right? So remember, when the system is the air inside the piston, if the system is expanding, then the system is doing work on surroundings, and then the W is the W of the system on the system is going to be negative, right? But on the other hand, when you are doing compression, right, the volume is shrinking, and then basically the surrounding is doing mechanical work on the system. That's why the W is positive, okay? And you always can think about correlate this dW and dQ back to the internal energy du, right? All right, so now you can kind of see, right, dV and dW, they have different opposite signs, right? So this is like how you can actually calculate dW. dW is going to be F dx, right? This you should already learn. F is the force, dx is the displacement. And then the force, right? Force here, in order to correlate the W and dx, right, we actually need to put a minus sign here, minus PA. P is the pressure, A is the cross-section area of this piston. Pressure times cross-section area give you the force, right? And then since dW, right, again, if dV is positive, then dx is positive, right? X is 0 here, then x is like moving this way. So dx is positive, but in order for your dW to be negative for the expansion process, we need to put a minus sign in the front, right? So dW is going to be minus PA dx, okay? And then you can move A, since A is constant, you move A inside the bracket, and then minus P dAx. And then dAx, AX is basically just like the volume of your system, right? So it's going to be minus P dV. So this is like dW is equal to minus P dV, okay? Now, talking about this P, pressure. The pressure is always going to be external pressure, right? So because we are talking about the pressure, the surrounding is doing mechanical work on the system. And then usually the external pressure is going to be constant, right? I mean, if you are talking about the surrounding being atmosphere pressure, then external pressure is 1 atm. If you are talking about like, you are exerting a certain pressure to compress it during that pressure application, you can keep that external pressure constant. So within this equation, dW is equal to minus PdV. This P is always, if you use P external in this equation, it's always going to be correct. Okay, so that's universal for all processes. dW is equal to minus P external dV. V is the system of the system volume. Okay. Now, in a particular case, right, which we call it's a reversible processes. And for the reversible process, what's happening is that your P external is always equal to P system. Okay, so then P external and P system can be used interchangeably. So in this case, you can use dW is equal to minus P system dV. So system pressure and system volume. Okay, now like when we have like P external equal to P system, meaning that it's system pressure is equal to external pressure, so this piston is actually balanced at all times. That means like your system is at equilibrium state at all times. And we will talk about this reversible processes is usually talking about like very, very slow processes. Basically, you are trying to compress or expand very, very slowly, and then by doing making the process very slow, you can actually ensure the system pressure is always equal to external pressure. Then you can use this equation to calculate. Okay, but in the end, right, it will also this equation is still true, right, because your external is equal to system. Okay, in this particular case for reversible processes, right? So to be safe, you can always just use dW is equal to minus P external dV. Okay. All right, just give you an example here. Like as we can come back to this piston air system, right? So you have air inside the piston, and this is your system. And then we have a latch, just like stop the latch to move, stop the piston to move, right? So you just fix the latch over there. So here it's not moving. Okay, you have external pressure. Let's say your external pressure is just atmosphere pressure, which is 1 atm. And then let's say at the beginning, right, you have P1, system pressure is 7 bar, and then volume is 0.1 meter cubic. Now you have external pressure, but you also have like pressure, exerted by latch, right? So essentially, this latch actually compensate the pressure difference and stop the latch there. Now, what we are trying to do, this is your original state or initial state. And then what we are now doing is that basically we open the latch, right? If we remove the pressure exerted by the latch, then right, your P1 system pressure is 7 bar initially, and then your external pressure, right, since you remove the latch instantaneously, the external pressure immediately drops to 1 atm. So 7 is greater than 1. So obviously you will think, right, this piston will move towards the right? So basically you are expanding the system, okay? Now, when you are expanding, then your volume is increasing, your pressure inside the system will slowly decrease, and then the system pressure is constantly changing from 7 bar to a lower temperature, to a lower pressure, right? So the system pressure is constantly changing during this process. But the external pressure is constant, right? External pressure at the beginning, when you release the latch, it's 1 atm. And then when you expand to the end, right, you are not like, it's still 1 atm. So external pressure is always 1 atm, right? So then it makes our calculation of that dW really easy. dW is minus P external dV. And then P external is constant during expansion, which is 1 atm. So you just like plug in into this equation since we need to calculate work here. So work, you actually need to take the integral from initial V1 to V2 minus P external dV, right? P external is constant, so you can move it out. And then here is basically V2 minus V1. So you plug in at the end, you will get like minus 10.13 kilojoule. And then coming back to check, right? Expansion, dW is smaller than 0, or W is smaller than 0 or negative. So here, right, W is negative for expansion process. So cross check, okay? All right, so hope by now you know how to calculate work. And then previously we already talked about the heat sign, right? And then if you have like W, if you have Q, you can figure out the change in internal energy, okay? All right, so now equilibrium state. So imagine you have like this latch, and then you release this latch, and then eventually, right, like I mentioned, right, the system pressure is continuously decreasing. And until when though, right? When will this latch stop? Okay, it will stop when the external pressure and the system pressure are equal. So meaning that when your system pressure drop down to 1 atm, right? So it's 1 atm on the left, 1 atm on the right. And then the pressure is balanced, right? When the pressure is balanced, then the latch cannot move, right? So basically, we say that final state is actually an equilibrium state, okay? Now, just like coming back to this, just like to state it out, right? Equilibrium state is a system at a equilibrium, meaning that if there is there is absence of change, as well as absence of any tendency towards change of any thermodynamic property of the system. So basically, after reaching this equilibrium state, your system in thermodynamic property of the system no longer change or no longer has any tendency to change. Okay, so this is the definition of an equilibrium state. Okay, so previously we said, right, T1 state 1, because we have latch, right, we are fixing basically we are fixing the latch, and then it's not moving. So this is actually state 1. And then we release the latch, right? And then basically the system pressure is now greater than external pressure. So the piston is starts to move, right? So during this moving processes, it's actually not at equilibrium. So this is equilibrium, but during the moving of the piston is not at equilibrium. It will reach another equilibrium state after sufficient time when this P2 actually drops to P external. So 1 atm here, 1 atm here, then it's like equilibrium again. Okay, so this is actually state 1, which is equilibrium. State 2, basically a new equilibrium state. And then the change between these two states is called process, right? And then within this process, the system is not at equilibrium. The system and the surrounding is not at equilibrium, okay? All right, so that's the definition of equilibrium state. Now, when we talk about equilibrium state, right? So basically this is state 1, this is state 2, and then associated with every single state, you have like different different thermodynamic properties, right? For example, your P1, T1, right? So this is your thermodynamic properties of your state 1. And then when you reach a different state, then you are actually having a P2, which is a lower than P1. And then you have a T2, right? So also different from T1. So these T2, P2, or T1, P1 actually define the state, right? So basically where it describes where your state is or what is your state condition, okay? So here we can just like say these thermodynamic properties are actually state functions, right? Because the thermodynamic properties defines the state, okay? So by definition, thermodynamic properties are properties of the substances that depend only on the present condition or state, but not the past history of the substances, nor the path it follows. Okay, so basically we are trying to say these thermodynamic properties actually just like define the state or depend on which state you are in, right? Either state 1 or state 2, but not dependent on the process, right? Or the change between states. Okay, so this is the process, this is like two different states. So for thermodynamic properties, we already talked about pressure, temperature, volume or molar volume or specific volume, and then internal energy. These are all thermodynamic properties, right? And then Q and W, Q is heat, W is work. And then these are actually related to the process, right? Depending on what kind of like process you are having, your Q and W might be different, right? So basically Q and W are not thermodynamic properties because they are path dependent and they don't define the state, okay? And then P, T, V, U, these are all thermodynamic properties which define the state, okay? Now, to better understand this process, or we can give you an analogy, analog, okay? So here, let's say you're on the ground level, and then you want to go to like 1, 2, 3, third level, okay? You can either take an elevator, right? You just like hop in the elevator and the elevator lift you up to from ground level to third floor, okay? And then you can also take stairs to go from ground level to the third level. Now, these are two different paths, right? One is through elevator, which you are not, performing any work or making too much effort, right? The other route is actually you are taking a lot of steps, right? And then basically you are doing a lot of work, right? So in this particular case, let's ask, is the final level a state function, right? So here we are on ground level, and then here we are on the third level. If I start here, finish here, no matter if I go from elevator or go from stairs, right? The initial level and the final level doesn't change, right? I can either be like, ground level at the beginning and then final level at the end. Same result, ground level here, third level here, okay? So the final level is a state function. So yes to this question. Now let me ask, right? Is the work that you perform a state function, right? So here, this is analogous to the work that you are performing here between state 1 and state 2, okay? So here, right? Here within the elevator route, right? I'm not performing any work, but for the stair route, right? I may sweat, right? After climbing 3 floors, right? So we are actually performing a lot of work. So the total amount of work that you perform during this process is different, right? Essentially 0 here, but a lot here, right? So is the work you perform a state function? The answer is no, right? So that's why if you go back to think about these thermodynamic properties, right? Temperature, pressure, obviously these define the system, right? And then define a state, right? Internal energy, molar volume, or specific volume, same thing, right? And then Q and W is really talking about the exchange, right, between the system and the surrounding. So basically these will depend on how they interact, right? So Q and W are not going to be thermodynamic properties because they depend on the path and they don't define the state, okay? So hope by now you can understand like the difference between thermodynamic properties here, PTVU, and the other non-thermodynamic properties, including Q and W, okay? All right, within this, these thermodynamic properties, we actually have 2 different types of thermodynamic properties. One is intensive properties. These actually are quantity independent. And then we have extensive properties. These actually depends on your quantity or depends on the total moles of the species that you have in the system, okay? So intensive properties includes like temperature, pressure, right? Temperature obviously doesn't depend on how many moles of the species you have in the system. Same thing with pressure, okay? And then molar fraction, right? Molar fraction in liquid, we usually use X, right? In gas mixture, we usually use Y to represent molar fraction. Molar fraction is unitless. So you would imagine it doesn't depend on the moles of the species. It only depends on the relative ratio between the species, right? And then V is molar volume, and capital V is we say molar volume. Okay, molar volume is gram per mole. It's already normalized to the amount of the species that you have. So it's basically an intensive property. And then U is molar internal energy. Okay, so these are all intensive properties. Now, when we talk about extensive properties, then we are talking about like, using this molar property, for example, and then times the total moles of this species that you have in the system. So in that case, we usually use U total to represent the total internal energy, right? So basically taking this U times the moles of this species, or the V total. V total is total volume of your system. So basically it's going to be your molar volume times the total moles of the species within the system, right? So these are extensive properties, depends on the moles of the species that you have in the system. And then intensive properties doesn't depend on the moles of the species that you have in the system, okay? All right, so now coming back to the state function or thermodynamic properties, right? The thermodynamic properties have 2 important characteristics, okay? So first, it only depends on state, right? Only because they define the state, right? So if you go from state 1 to state 2, right? The thermodynamic property for state 1 are fixed, right? Thermodynamic property for state 2 are fixed, right? And then when we are talking about the change between these two states, like then the M, let's say M is a particular thermodynamic property, you are focusing on delta M changing the this particular thermodynamic property going from state 1 to state 2 is just equal to final minus initial, right? So M2 minus M1, okay? So this change is going to be fixed regardless which step you choose, right? Which process you go with, right? You can go this way, you can go this way, you can go all the way this way. But the change between these two states will always be the same, right? Delta M is equal to M2 minus M1. This is similar to the elevator stairs example in the previous slide, right? No matter whether we take the elevator or the stairs, the change in the levels, right? Floor levels is always going to be 3 minus 0, which is 3, because we just did that like change, right? So characteristic and one characteristic change between states, you can use this equation, final minus initial, to calculate the change in state functions, okay? Now, building on this, right, then we can actually take a step further, right? We can actually do a closed integral of a state function, and then you can quickly realize it's going to be equal to 0. So here, what we are trying to say is that you go from state 1 to state 2, and then you go back, right, from state 2 to state 1, either this way or the back, or all the way like this back, okay? Regardless like which route you take, as long as you like go from here ends here, then your change is going to be 0, right? This is called the closed integral. Closed integral is going to be M initial minus M initial, which is essentially 0, right? So when you have a state function, then the state function, you will quickly realize the closed integral of dm is equal to 0, okay? All right, so now these are different types of thermodynamic properties, and then the important characteristics of a thermodynamic property or of a state function, okay? And we will come back to use these these characteristics to actually help you understand when we are talking about the enthalpy, which is your H, right? H is also a thermodynamic property. And then later we will also talk about entropy. When we talk about second law, entropy is also a thermodynamic property. And then because they follow these kind of like characteristics, okay? We will come back to that later, okay? All right. So speaking of enthalpy, right? So now this is like the reason why we care about enthalpy, okay? And we will quickly introduce you to what enthalpy is. And the reason why we want to introduce enthalpy is basically because we want to approach a real-world chemical engineering processes, right? Which often run at a steady state, right? If you go to a chemical plant, it's running 24/7, right? It's like all the, you have everything is running continuously, right, at a steady state. And then that's called like process control. You need to monitor the process parameter, make sure they are at a steady state, right, to ensure product quality, or to ensure just like everything is within the specifics, okay? All right, so now if you take a look at this particular system, right, you always have like, liquid water pumping inside the boiler and then evaporating and then cool down, right? This is like, it's a continuous process because you want to continuously, let's say, generate energy, okay? So as you imagine, you are dealing with a steady state process, right? And then here for condenser and boiler, really we are talking about the heat exchange, right? The heat goes in this case, into to your liquid water, and then basically if you pick liquid water or water vapor as your system, and then basically this liquid water curve absorb heat from the surrounding, right? And then the condenser is basically this water vapor give out heat inside the condenser, right? So this is the heat that is being involved in this particular steady state process. And then if you talk about pump is like, basically you're pumping the liquid inside the boiler by doing mechanical work to the system. And then turbine is basically your vapor coming in, push the turbine. So actually the vapor is actually doing work on this on the surrounding, right? So giving out work. And then these are usually called shaft work, right? Now, if you just like draw a measuring box, and then you are picking the liquid or the vapor water, specifically water as your system, right? And you can imagine this is like a steady state system involving the water, right? The surrounding is doing giving heat or taking heat away from the water, and then the pump and turbine are doing mechanical work or vice versa, right? So how do we analyze this particular process? Okay. Now this is like how we can simplify this analysis. So let's imagine consider steady state flow chemical engineering processes, right? So here you can actually use just like a square. Let's say this is just like heat exchanger, could be boiler, could be compressor, right? So this is like representing you have like some heat exchange between the system and the surrounding. And then here system, we can actually pick, right? Within this flow system, we actually pick 1 kilogram of fluid. So basically we are monitoring this 1 kilogram of fluid. When it goes from here all the way to here, what's happening to this 1 kilogram of fluid? Fluid means, let's say, water, okay? It could be in the liquid state, could be in the vapor state. I don't know, right? But that's why we say we pick 1 kilogram of fluid as your system, okay? And then if you imagine, right, everything else is your surrounding, okay? And then like go through a heat exchanger, and then go through even turbine or pump, right? Having some mechanical work, right? Q and W. And then you go all the way here, right? If we draw an imaginary box, and then you can actually set, this is your initial condition or state one, and then this is your final condition or state two. And then let's say your state one has a pressure one, P1, and then V1. V1 is the molar volume of this fluid at this particular state, right? So P1, V1 related to state one or the cross-section one. And then P2, V2 related to cross-section two or state two, okay? Now we just need to understand, right? Apply the first law of thermodynamics to this particular steady state system, right? So when we apply this, right, apply the first law at any instant time for 1 kilogram of fluid, okay? Again, this is your system. 1 kilogram of fluid is your system, right? So delta U is equal to Q plus W, again, ignoring kinetic and potential energy, right? So delta U just equal to Q plus W. Q is again heat transfer through the heat exchanger. Work is work done by the system, right? And then now this work actually have two forms, right? One is the shaft work. Shaft work is basically down through the pump or through the turbine, okay? So walk down through the engine, right? Network output or input, right? So when we are talking about steam turbine, then your WS is going to be negative because your system, your water, right, is doing work on the steam turbine to convert mechanical work into, electricity or something else. Okay, so WS is negative. But for gas compressor or liquid pump, your shaft work is going to be positive because your external engine is actually giving the system energy, or I mean, doing work on the system. So you have work input to increase the P, okay? So shaft for steam turbine, usually, right, you have like vapor condensing to liquid, so usually your pressure is going to drop, okay? And then like when you are doing the pump or compressor, your system pressure is going to increase, right? That's why you have to use relationship, okay? Another form of this work is actually the flow work, right? Flow work is due to the change in your pressure and molar volume, right? So for W flow, you have like flow in is P1 V1, and then flow out is going to be P2 V2, okay? And then by convention, we just specify if we have a flow in, okay, usually it's positive, right? That's why you have positive here, P1, V1. And then if it's flowing out, then it's negative. So it's going to be minus P2, V2. So if you pick a box like this, right here, you're flowing in, you're flowing out. So your W flow is going to be P1 minus P2 V2, P1 V1 minus P2 V2. And again, P1 and V2 are molar or specific volume of the fluid at sections 2 and 1, okay? 1 and 2. All right, so now we define the system, we pick the box, and then we can actually write the change between position 2 and 1. So delta U is equal to Q plus WS plus W flow. And then W flow, you just plug in P1 V1 minus P2 V2 plus WS. And if you rearrange the equation, right? So put a minus sign in front, P2 V2 minus P1 V1, and then basically Q plus WS. And again, this P2 V2 minus P1 V1 is just like delta PV, right? So delta PV minus sine steal. So final minus initial, delta PV, okay? But you have a minus sign in front. And then if you rearrange this equation by moving this to the left side, so delta U plus delta PV, you can combine things, right? Delta U plus PV is equal to Q plus WS. Now here come our definition of the enthalpy, okay? Enthalpy H, we usually use H to represent enthalpy. Enthalpy is equal to internal energy plus PV, okay? P is the system pressure, V is the system molar volume, okay? Or volume. And then if you define enthalpy here, right, then your delta H, right, is just equal to Q plus WS, right? And then delta H is basically changing enthalpy. It's going to be like final minus initial, right? Final enthalpy H2, and then initial enthalpy H1, right? So delta H is equal to H2 minus H1 is equal to Q plus WS, okay? And then we will convince you that H or enthalpy is also a thermodynamic property or a state function in our next lecture, okay? Now, we have already studied like the change between section 1 and section 2, right? Like I mentioned, we are running this chemical engineering processes at a steady state, right? So when we are talking about steady state flow process, right? Instead of picking 1 kilogram of, we were picking 1 kilogram as your system, right? Then this 1 kilogram is actually flow, like the flow rate is actually, you can, per kilogram per second, right? You are pumping in a specific amount of like kilogram of the substances into the whole flow, right? Then you basically just like introduce a flow rate, mass flow rate here, right? So you have delta H still the same as previous slide. And then you just times a mass flow rate. So basically kilogram per second, right? And then usually if your heat exchanger and turbine are operating at a specific, power or, then you will have a specific heat flow rate, right? Heat flow rate Q, right? You have dot on top, dot on top, dot on top, or shaft engine power, right? At a specific rate, so watts or joule per second. So on the left, you have per second. On the right, you also have per second or watts as unit, okay? So here, delta H times the mass flow rate of your fluid equal to the heat flow rate plus the engine power, right? All right, so at the end of each lecture, we also have like additional slides. If you have time or interested, you can actually read them, but usually they are focusing on the derivation of a particular slide in this lecture. So that concludes our lecture 1. So hopefully you learn how to define the system surrounding and then the interaction between the system and surrounding, and then we really talk about the first law of thermodynamics, which means the energy is conserved, right? And then we also introduce enthalpy, which is equal to U plus PV, right? Enthalpy H, that's the definition of your enthalpy, okay? All right, we will come back to our next lecture. We will talk about the second law of thermodynamics and entropy. Okay, all right. That's it for today. Thank you.